Hi, I did an unboxing video of this UNI-T UPO1204 200 MHz bandwidth digital storage oscilloscope last week, and since then I have spent quite a bit of time combing through the user manual and trying all the features over the last few days. There are some bugs and annoyances which I will point out along the way, but overall I have to say this is a very solid oscilloscope from UNI-T, and if you have one, I think you will draw the same conclusions as well. If you missed that unboxing video, I will leave a link up there so you can go and check out. In this video though, we'll do a deeper dive on some of these features so you can be the judge yourself. Depending on how much time I spend talking through these features, I may need to do a separate teardown video. By the way, the product link is in the video description below, as usual, for those who are interested. One thing I forgot to mention in my previous video is that the UPO1000 series all have a vertical resolution of 8 bits instead of the 12 bits that some of the more expensive scopes offer. Of course, with 12 bits you would have higher dynamic range, and that is useful for some applications. One use case I can think of is analyzing small signals in the presence of large signals, such as noise. But for most of the work, especially for hobbyists, 8-bit remains sufficient. So the first thing we're going to do is verify its bandwidth claim, and that's something that most people wanted to see. The sampling rate of the UPO1000 series is fantastic. It is specified at 2 gig samples per second. So we know the sampling rate would not be the limiting factor, and in fact, this sampling rate can comfortably support up to 300, even 500 MHz if the scope's front end is capable. For the first test, I'm feeding the RF output from my HP8642B RF signal generator, which is humming in the background, to channel 1 with this 50 ohm feed-through terminator here. You can see that, so that the impedance would be properly matched between the scope and the signal generator. So I have adjusted the RF output so that I have a 0.1 volt roughly peak-to-peak reading on the oscilloscope. Let's take a look here. And actually it's a 1 volt. The reason is because we have this times 10 enabled. Let's actually adjust that. So let's go here, Pro, and right now we are just using a coax, so it's times 1. So let's go back to channel 1 here, and now we should have this 100 millivolts that I mentioned earlier. If you do the calculation, the RF output power level would be around minus 16 dBm to get this 0.1 volt peak-to-peak reading, but currently because of the loss in the cable, you can see here, we have an output of roughly minus 15.2 dBm. So that is actually normal because there's a little bit of cable loss. Anyway, so let's concentrate on the scope here, and I try to adjust the camera angle so you can also see the signal generator in the background. And currently the frequency output from the RF generator is at 50 MHz, which is well within the bandwidth limit of this oscilloscope. And now let me ramp up the output frequency from the RF generator and see what we get on the oscilloscope. So this frequency, and let's go straight to 100 because we have 200 MHz bandwidth and that's more than sufficient. So let's do 100. And you can see we are at 96 millivolts, so that's well within the 0.707 bandwidth limit. And let's keep increasing to 150. And you can see no issues. And let's keep increasing to 200. So now we're at 200 MHz, and you can see we still have 84 millivolts. Let me just zoom in a little bit. You can see that. So clearly this is still within the bandwidth limit. And let's keep increasing. Let's do 200. Let's see here. $250. And right now we're at 250 MHz. You can see we still got 75 millivolts. So clearly that is still within the 3 dB bandwidth. And you can see now the frequency output is sitting at 250 MHz. So let's increase a little bit more and see if we can push the limit a little bit. So now I am increasing it to 300 megahertz. And I didn't see when it dropped off, but we still got about 69 millivolts, which is just below the 3 dB bandwidth, as you can see here. And you can also see that the frequency counter picked up the frequency with no issue. As you can see here, the 3 dB bandwidth is well above the specified 200 MHz, and there's no degradation in the captured waveform either. And just for curiosity, let me keep increasing the frequency output and see if we can still capture that stable waveform at a higher frequency. So now I'm increasing the frequency to 350 MHz. Of course, you can see that the amplitude dropped quite a bit, but we're still able to capture that waveform. Now let me increase the frequency to 400 MHz. And of course, the amplitude dropped to 47 millivolts, but we're still able to capture the waveform with no problem. And it's actually quite impressive, as the frequency counter, as you can see, still measures roughly 400 MHz. So that's well beyond the specified 200 MHz already. And let's keep increasing the frequency to 450 MHz. Yeah, at this point I would say this is probably approaching the upper limit of the front end, because you can see that the amplitude is dropping significantly, and also the waveform started getting a little bit fuzzy. For all intents and purposes, I think the scope is designed obviously up to 200 MHz, but you can definitely use it, especially in single channel mode, to observe a signal of much higher frequency. At least you can get an idea of what the signal looks like. By the way, you can see here, the hardware frequency counter is not able to catch up. Right now we're at 450 MHz, but the captured frequency is only at 365 MHz. Actually, let me go back. I don't remember where we lost that tracking here. So let's go back to... Okay, so I think it's right around 400 MHz that it was no longer able to measure the frequency, but we can still push a little bit, I think. So let's go to, let's say 500 megahertz here, which is half gigahertz. Yeah, so definitely we're not able to see the signal anymore. But clearly at 450 megahertz, the observed signal is still very useful. And just to show you that, you can see here on the signal generator, we are indeed outputting a 450 MHz signal at minus 15.2 dBm. And now I have adjusted the output frequency back down to 200 MHz, and according to the specifications, the 2 gigasamples per second sampling rate is only when you have a single channel enabled. And when 2 channels are enabled, the sampling rate drops to 1 gigasamples per second, and with 3 or more channels, the sampling rate further drops to 500 megasamples per second. So the bandwidth specification must have taken the maximum number of channels into consideration already. So let's actually verify the 200 megahertz bandwidth measurement with more channels turned on. So let's turn on another channel. So now the sampling rate halves, and you can see that we actually don't have any issue capturing that signal. And let's enable another channel. And you can see that channel 1 measurement remains unchanged. Right now, keep in mind, the sampling rate drops to 500 megasamples per second. So in theory, I should be able to push the input frequency a little bit higher and still be able to see that stable waveform, because we are still over the Nyquist frequency currently. So let's enable it to 240. And you probably will start seeing aliasing above that. Yeah, so right now you can see that the specification is definitely taken all 4 channels into consideration. As for example, right now I have all 4 channels on, and the frequency right now is 220 megahertz, and you can see actually it's 219 megahertz, but you can see now it's 220, and you can see that the captured waveform started to degrade quite a bit. But at 200 megahertz, we don't have any issues. So let's go back down to 200. And you can see that the waveform captured remains very, very clean. So this is different than a lot of the cheaper scopes where the specs are overly exaggerated. This one actually is very conservative. It tells you the bandwidth with all 4 channels enabled. But as you can see earlier, with a single channel, you can push that number much higher than what is specified. Of course, as I have mentioned in the past, measuring the bandwidth this way using a RF generator for digital oscilloscopes may not be the best and most accurate way because the front-end amplifier may have programmable gains, which could be used to compensate the roll-off to some degree. Now, of course, we don't know that. So a more accurate way to derive the bandwidth is to measure the rise time. For that, I have an avalanche pulse generator, which is capable of generating pulses with rise time in the hundreds of picoseconds range, which is sufficient to verify the bandwidth of scopes up to at least 1 GHz. You can see that we have the avalanche generator here, which is turned off currently, and is connected to the scope via a 50 ohm termination here, so the impedance is matched. So now let me turn it on. And before I do any adjustment, you can see just how fast the update rate of this scope is. So now let me try to auto-acquire this. Of course, I don't think I can, but let's try it. Yeah, I cannot acquire that signal, and there's some crosstalk between channel 1 and channel 2. So let me put it down here, and let me first zoom it in, and it will manually adjust the time base here. So let's adjust the time base here. You can see we already have a stable signal. Let me put it down here. And this is our signal here. So let's put it in the view. And currently the horizontal scale is at 1 nanoseconds per division. So let's actually use a couple methods to measure this. And the first one I would like to do is just use a built-in measurement. Let's see if we can do that. So let's enable all parameters. And let's take a look. So let me zoom in so you can see the screen a little bit better here. And you can see here we have this parameter called rise, and that's the rise time. So right now it's measuring at roughly 1.2 nanoseconds. So if we use that 1.2 nanoseconds figure, we will derive a bandwidth of roughly 290 megahertz. Of course, this number changes a little bit, so let's actually use another method to verify that. And next, let's use cursor measurement to just verify the numbers we saw here. So let's get rid of the parameters here. And go to cursors. Let me adjust the cursor here. So now keep in mind this is just approximate as we have a little bit of wiggle room here. So let's see. I would say this is probably close enough from 10% to 90%. As you can see here, the measured rise time is at roughly 1.24 nanoseconds, which translates into a bandwidth of roughly 280 megahertz. Now that is pretty consistent with what we had with automatic measurements. While we're measuring the avalanche pulse, let me show you the segmented sampling memory capability of this scope. Now, since this scope is so feature-rich, it is impractical for me to go through all the functionalities. So what I'm going to do here is to concentrate on a few important features that you need to know about when deciding on your next scope. Anyway, segmented sample memory can be very useful in capturing low duty cycle signals like what we have here. Right now, for example, the frequency is at 33, roughly, kilohertz, and that's the repetition rate. But the signal you can see here is only at a few nanoseconds in width. Or you can use segmented memory to measure burst signals with long idle time in between. So even if you have a lot of sample memory, if you're sampling at a very fast time base, because say you're trying to capture a very narrow pulse, like what we're doing here, then you're not going to be able to store that long of a duration, even with high memory depth. For instance, if you're trying to capture a pulse train of several nanoseconds, and the idle time is 1 second, then you are most likely only able to capture a single pulse train in memory. So this is where segmented sample memory comes into play. As the name suggests, it essentially divides the sample memory into many segments, and the number of the segments is essentially dependent on the memory depth you choose. And this makes sense. As you have a fixed size memory pool, the smaller the memory depth, the more segments you have. Anyway, with these memory segments, each segment can capture the waveform independently, and you can then scroll through the captured waveforms frame by frame. So let me demonstrate that here. Let me zoom in a little bit. And let me get rid of the cursors. Let's see here. Acquire. By the way, right now we're at 7K, the memory depth. You can see how fast the update rate is. Of course, if we change it to, say, 70K, and you probably didn't see a difference. And if we go to all the way up to 56 meg, you can see that the update rate definitely slows. Anyway, let's change the memory depth back to, let's say, 70K. And let's come to fast acquire. And here is where we can do the segment memory. And for example, if you see here, we have essentially right now, because the memory depth is at 70K, we can capture 800 frames. And so let's start it to capture that. Let's hit record. And you can see we already recorded all the 800 frames. Now let's play back. And now we're just playing back automatically. But if I stop the frame here in the middle, and we can use the scroll wheel to actually play back frame by frame. So essentially we have 800 samples of this waveform, which is actually a very, very powerful tool, because now you can see the differences between each of the captured waveform, and without the segment memory, you wouldn't be able to do this. And just to show you the relationship between the number of frames and the sampling depth, we can come back here and set that sampling depth again. So let's start running, and let's go to acquisition. So let's do memory depth, let's say 700K this time. And let's go back to acquire again. So let's do fast acquire, and this time let's see how many frames we have set. You can see now we only get 80 frames because the memory depth had increased. So let's do that again. So let's go fast acquire and record. So now again, the sampling has stopped. We can use the scroll wheel to play back the actual captured waveform here. This feature traditionally is only on very high-end scopes, but now of course you started finding this in some of the more mainstream scopes like this one, which is really a welcome feature. The UPO1000 series has an auxiliary output BNC port, and it can be configured for different outputs. So let's actually show you here, and we go to utility. Here we have IO set, and here you can see we currently have the output to output a trigger, but if you want, you can output pass-fail and DVM. Anyway, so that's a very useful feature here. And with this trigger output, we can use it to get a sense of how fast the display update rate is for this scope. In the specifications, it is mentioned that the waveform update rate is up to 150,000 waveforms per second, up to 500,000 waveforms per second in fast acquisition mode. But it didn't say how this number was derived. Regardless, we can use the trigger rate to infer how fast the actual update rate is. Of course, the triggering rate is dependent on many factors. To get the fastest trigger rate, you will need to be on the fastest time base, like what we have here, 1 nanoseconds per division. And the memory depth and display method also affects the triggering rate. So let's actually take a closer look. Here I'm using a DreamSource Labs portable oscilloscope to measure the trigger waveform output from the auxiliary port. You can see that the waveform update rate currently is measured at 36 kilohertz or thereabout. And of course, we do have some dead time. Let's stop this. And you can see that currently we're at 5 milliseconds per division. So the dead time is roughly at around 5 milliseconds, and which is actually normal for most of the scopes. And it depends on the implementation. The sampling is not going to be constant. Also, right now, the scope currently behind here, we set it the fastest sampling rate of 1 nanoseconds. If I reduce the sample rate, of course, you can see that the captured waveform update rate is going to be decreasing. So let's turn it back to 1 nanosecond per division. And of course, the update rate depends on many factors, as I mentioned earlier. For example, if I move the controls here, obviously that will interrupt your update rate, as you can see here. Also, the memory depth plays a key role here. So let me show you. If I go back here, acquisition, right now we're at memory depth, 7 kilo points. And if I change to 70, you can see that the memory depth changed it to roughly 16 kilohertz. Sorry, not memory depth, the sampling rate. And if I go down to 700K memory depth, you can see that it further reduces to 2.5 kilohertz. So let's actually go all the way down to 56 meg. And you can see here, we're only sampling at about 35 Hertz, actually 34 Hertz. So that's a relationship between memory depth and your sampling rate. Of course, the triggering rate is not only just dependent on memory depth, also depends on other factors as well. For instance, how the display is rendered also impacts the triggering rate. So let's take a look at the display here. So right now, for example, the display type is vector. So let's change it to dots. And you will see that the sampling rate actually increased from 35 to roughly 50 kilohertz. So that's definitely something to keep in mind. Now let's take a look at the single shot capability of this oscilloscope. You probably have seen me doing this demonstration many times with different oscilloscopes before, but one thing I wanted to show you is how easy it is to navigate the captured waveform on this scope. For the testing, I have a power supply outputting roughly 10 volts, and currently the output is turned off. Let me turn on the output and do a single shot, so we can capture the power on characteristics of the power supply. For this capture, the horizontal rate is set at 100 milliseconds per division. So let me enable the single shot, and let me turn on the power supply. And you can see we captured the waveform with no issues. Actually, I think the sampling memory depth currently is still set at 7K, so let's take a look at that. I wanted to increase that a little bit, and let's do it again. So now we captured another signal snapshot. Now let's try navigating through this waveform. So let me decrease the time base, and let's start it moving it around. Of course, you can always use the horizontal to move it around, but in this case, we actually have a neat feature here. So if you press on the navigate, you will see that the arrow keys here are highlighted. So what we can do is use this to, for example, automatically zoom it through. And you can double press it, it will go faster. And you can press the other way around and it will go the other way around. So this is actually a neat way to navigate through the waveform. So this, in my opinion, definitely is a neat way to navigate the captured waveform. And now let's take a look at an FM signal. Here I have a signal coming from the UNI-T UTG962E signal generator, and it's a 20 kHz signal with a 10 kHz frequency deviation, and the modulation frequency is set to 100 Hz. And the reason I choose 100 Hz is because you can see the update rate from the captured signal. And as we have demonstrated earlier, there is a trade-off between the update rate and the memory depth. So right now we're at 7K, and let's take a look at the effect of the memory depth. So if I just cycle it through here, you can see the update rate gets slower and slower. And now we have switched to an amplitude modulated signal. Now, AM signals are harder to trigger, and most of the scopes can't produce a totally stable captured waveform. And here you can see that the waveform is moving back and forth a little bit. Now, I can certainly adjust some of the trigger levels and fine-tune it so that the waveform can be a little bit more stable. Of course, I can also do hold off and other techniques to make it more stable. But what I wanted to show you is the external trigger capability of the scope, and it comes in handy in situations like this. And now I have connected the signal generator's sync output to the external trigger input BNC at the back of the unit here. And let's set it up here. So let's go to trigger, and currently we're setting the trigger source to be channel 1. And let's set it to external. And you can see immediately after we enable the external trigger, we have a very stable signal. So the external triggering capability of the scope definitely comes in handy in this situation. And by the way, here is one of the bugs I found, and you can clearly see it here. The screen is pulsating. Now, because the scope has an intensity graded display, some scopes call it digital phosphor, and in this case, the UPO1204 series calls it ultra phosphor. Because of this, you can see the gradient here, but you also see the pulsating effect. I'm actually not entirely sure why this is happening, but definitely something for UNI-T's engineering team to take a look and address perhaps in a future software release. But otherwise, the intensity gradient looks beautiful. Let's change the time scale. You can see that it looks absolutely beautiful. You can do extensive mathematics with this oscilloscope. As a demonstration here, I have a signal coming into channel 1 that is 1 kHz sinusoidal, and another signal that is a 100 kHz sinusoidal going into channel 2. So let's take a look at what we can do with these two signals using mathematical functions. So now I just enable the math channel here, and you can see we're doing channel 1 plus channel 2. That is Not very interesting. Let's try channel 1 times channel 2. Aha! Does it look familiar? Well, in fact, we just produced an amplitude modulated signal mathematically using channel 1 times channel 2 here. So, of course, we have more capability here. Let's take another look here. Actually, let's change to other advanced functions. So you can see here, we are actually able to build our expressions. And this is actually quite powerful. So let's say we want to do channel 1. Let's do plus. Let's see here. Maybe we want to do the logarithm of channel 2. And let's hit apply. And you can see that's actually what we're looking at. This is the mathematical function that we just built. The FFT capability of this scope is actually quite powerful, and it allows you to do some rudimentary spectrum analysis. So let me demonstrate here. So for the input, I currently have a signal coming in from the signal generator. It's a linear ramp signal, ramping up the frequency from 1 kHz to 2 kHz over the duration of 60 seconds, and it just repeats. So let's take a look at the FFT of the signal here. So I came to FFT, and I had set up the parameter already, and let's actually take another look here. So the FFT, you can see that that's the function, and parameter set. Actually, currently I'm using the waterfall. By the way, you can also do the full FFT. You can see that that's just display the FFT overlaying the channel here. And let's do the waterfall display, because that's the coolest one I want to show you here. And there is a little bit of bug here. Every time you change the range, it appears that the setting actually is getting reset. So let's actually change that back here. So for the parameter set, let's see what we can do here. Frequency range. And right now the maximum frequency is too high. So let's change it back to, say, let's do 10 kilohertz. 10, 1, 0. Kilohertz. And now we can see the 3 peaks. And over time, the waterfall graph will build up, and you can see clearly we have the 3 peaks showing here. Now, that's a very powerful feature here. Unfortunately, as I mentioned earlier, if you change anything else, for some reason it doesn't remember the setting of your end frequency here, and that's actually quite annoying. And I just changed the end frequency to 20 kilohertz, so you can see a little bit more details in that FFT plot here. And I have to say though, the implementation is a little bit buggy, and I'm hoping UNI-T can fix the value not persisting issue in the future, so that it would make this feature far more useful. And now let's take a look at the Lissajous figure. For that, I'm inputting 2 signals. Those are both 1 kHz from channel 1 and channel 2. So let me enable the XY plot here, and you can see we can plot XY against any of the 2 channels here. So let's do channel 1 and 2. So now you can see we have the Lissajous figure. And one benefit of this scope is that you can actually measure the phase angle between the 2 channels. So let me turn on some measurements here. And you can see as soon as we press cursor, we are able to measure the waveform and currently the phase angle between the 2 channels. And we're measuring at roughly 26 degrees. So let's actually change the phase angle, and let's take a look at what we got on the screen here. So let me go down to phase. Let me just change one of the waveforms here, and you can see that as I change the waveform, the measurement changes as well. So that's actually a very useful feature in my opinion. So now let me change the frequency of one of the signals here, and we will see what we got on the screen here. So let's change it to 2 kHz. In fact, let's do this. Let's do 100 Hz at a time. So 100 Hz, 200 Hz, 300. And you can see that the update rate is not the fastest, but nevertheless is sufficient to show the different relationships between the 2 waveforms. And by the way, I think this scope uses the same case design with some other higher spec scopes, as some of the functions are not enabled on the scope, which is a little bit annoying. You can see that, for example, if I press Gen, and it will tell you that it's not supported, only the MSO 1000 series is supported. And similarly, if I press digital, and you can see that this button essentially does nothing on this scope either. I know this video is running a little bit long, but before I wrap up this video, I do want to show you one extra feature, which is the protocol decoding capability of this oscilloscope. And right now I have this Arduino board outputting a hello world message through the UART. So let's take a look at how we capture that. Let's go to menu on the trigger here, and you can see the trigger type here. We actually have protocol here. So we can actually trigger on the RS-232. And of course, we can support I2C and SPI because we have 4 channels here. So let's do RS-232. And let me zoom in a little bit so you can see it a little bit better on the screen here. And let's take a look at the parameters here. By the way, this is also a little bit buggy, and once you power off, for some reason it doesn't remember what you said previously. So that is actually quite annoying, but I'm sure that UNI-T engineers can take a look at this and probably fix it in a future version. Anyway, so let's go to the baud rate. We have 9600, and polarity, I don't remember if it's positive or negative. We'll take a look later. But the data bits is 8. And you can see that the default setting is actually not very standard. So not entirely sure why it is the case here. But let's enable the bus output here. So now you can see we have decoded signal. Type needs to be ASCII. So we can see what we're capturing. And right now I can tell you this is actually not correct just yet. So I think the polarity is positive, I believe. Yep. And let's just zoom it out a little bit. You can see we are capturing that hello world. Of course, right now it is not stable because we are not triggering on the correct spot. I think to set the trigger, we have to go back to the trigger menu here. And let's just see here, parameter set. Yep, when. Okay, so here, when data. Let's see if we can figure this out. So I think we can set it to 20. Yep, now you can see we got a stable trigger here. So let me get rid of the menu. You can see, let's zoom it out a little bit. You can see the hello world here. Now if I zoom it out a little bit, you can see the hello in front of it as well. So this is just a quick demonstration of the protocol decoding capability of this scope. Alright, that's pretty much all the major features I wanted to show you in this video. Now there's still a lot I haven't shown you yet. For example, you can access the oscilloscope via Ethernet connection on your computer via browser. Also, you can remotely control the scope via skippy command from your computer as well. If there are any interests, please let me know. I will definitely do another video on these features. I'm still planning on doing a teardown, but it will probably be in the next video. Well, I hope you enjoyed this review and learned something about this UNI-T UPO1204 oscilloscope. If you liked the video, please remember to give it a big thumbs up and remember to subscribe to the channel for more videos like this in the future. Your participation makes videos like this possible. Thanks for watching, and I will catch up with you next time.